Okay, the point of this screencast is to provide a qualitative conceptual overview of a portion of the material covered in the Module 3 PowerPoint. The version I'm covering, version I'm covering today has a May 4, 2016 timestamp. The intention of this is not to delve into the mathematical details. In fact, I'm intentionally going to avoid the mathematical details. This screencast is supposed to provide an overview, emphasizing background material and the principles that I want you to understand. Subsequent screencasts will delve into the mathematical details. Those will be broken up into single or sets of closely related mathematical derivations. This screencast is intentionally, again, avoiding the details and especially avoiding the math and trying to let you know what it is you're supposed to understand. What's the big picture? A lot of the fluorescence material is described nicely in the Lackowitz's book, Principles of Fluorescence Spectroscopy, which I call the Lackwitz Fluorescence Bible. So there's citations to that book at the relevant portions of the screencast. Anyway, with that, we'll get on with it. Spectroscopy, it looks at the interaction of light with matter. So obviously we need to know a little bit about light or remember some of the key features of light. Light is characterized by its wavelength and its frequency. The product of wavelength and frequency is the speed of the light wave. So an important point is that because in a vacuum, the speed of light is fixed by physical laws, a given frequency of light corresponds to a given wavelength. Because the product of the two has got to be a constant. As frequency changes, wavelength changes reciprocally. In a vacuum, light will move at a speed of about 3 times 10 to the 8th meters per second, or 3 times 10 to the 10th centimeters per second. And again, because the product of the wavelength and the frequency has to be that constant, increasing frequency means decreasing wavelength and vice versa. So that means in a given region of the ultraviolet spectrum, a given region of the electromagnetic spectrum will be characterized by some specific range of frequencies. And that range of frequencies will correspond to a specific range of distance. So in given region of the electromagnetic spectrum, there will be a characteristic frequency. The frequency will set the time scale, right? The time for one oscillation of the light wave to pass a point will depend on the frequency. That will set the time scale. That will be important in terms of what time scale of events we can probe in matter using light of a given frequency. It also sets a length scale. The length scale is also quite important when we're actually using light to visualize things. So we won't be talking much about that. Visualization is the area involves different kinds of microscopy and also diffraction. We don't have time to talk about that stuff this semester, so we'll be focusing on spectroscopy. Okay, another key point of light is that the energy of a photon is quantized. And a light of a given frequency can only transfer energy in a quantized amount equal to the energy of the photon. The energy of the photon is given by the product of Planck's constant times the frequency. So at a given region in the electromagnetic spectrum, it will have a given frequency, and that means the photons will have a given and specific energy. Planck's constant is sometimes divided by 2 pi because well, when you get into wave physics, of course, waves involve trigonometric functions. Trigonometric functions are convenient to express in radians. So it's convenient mathematically often to divide the Planck's constant by 2 pi. That gives a constant called h bar. So you will see that as you look at spectroscopy literature. So it is interesting to pause and think about the lengths and time scales involved in different parts of the electromagnetic spectrum. The light waves that biochemists and biologists, biophysicists use tend to be between the infrared region and the X-ray region of the electromagnetic spectrum. In the infrared region, the frequency of light is on the order of 10 to the 12th waves per second. So that means the time scale of a single wave is 10 to the minus 12th, which would be a picosecond. As we get to the X-ray, higher energy region of the spectrum, the frequency will go up to 10 to the 18th. So the time scale will get even much shorter. The length scales of X-rays are on the order of 10 to the minus 10th meters. And so that is getting down to the level of single angstrom distances. So that is basically the length scale of atoms and small molecules. When we go to the visible region, we have frequencies on the order of 10 to the 15th waves per second, which means timescales on the order of 10 to the minus 15th, or femtosecond timescale. That will be important when we talk about spectroscopy. And the wavelength there is, on the order of microns. So in the visible, just submicron. So those are important things to keep in mind, important sort of points of reference. Presumably you knew all of that, but just make sure it's fresh in your minds. Okay, this is another view of the electromagnetic spectrum. It has some different information in it, but it's basically the same point. If we were talking about microscopy or diffraction, we would be talking about the limitations in terms of the size of things that you can visualize with light of a given wavelength. Ultimately, there's something called the diffraction limit that is related to something called Bragg's law for diffraction of light waves. I'm going to skip over that for now. Because we don't have time in this course to discuss diffraction or imaging, but we'll point out in passing that light of a given wavelength is only able to resolve spatial structures down to a certain size. And so that's another reason why in biophysics and in physical chemistry, we use light and electromagnetic radiation in different. We use electromagnetic radiation from different regions of the spectrum, depending on the size scale that we are attempting to visualize things. Okay, and then this slide shows some useful points of reference. Gives you some numbers. What's the wavelength of, for instance, green light in the 500 nanometers or 5,000 angstroms? What's the diffraction limit on that then? How small a thing can you see with visible light? Remember, there are 10 angstroms per nanometer. A water molecule is about 3 angstroms roughly in its diameter. Effectively, protein is 20 to 100 angstroms. Copper K alpha X-rays have a wavelength of about 1.54 angstroms. This stuff is all important to keep track of if you want to sort of understand biological systems. Well, if you want to use biophysical methods to probe biological and biochemical systems deeply, you need to know some of these numbers. So there's a useful compilation here that comes actually from a site called bionumbers.org. Okay. Now, so let's just recall, light is a propagating electromagnetic wave. Well, light, of course, has dual characteristics. Both it has wave characteristics and particle characteristics. The particle characteristics we talked about before, they're reflected down here. The particle characteristics are reflected in the quantization of the energy in a light wave. Again, light of a given frequency can only transfer energy to another object in quantized units given by the product of Planck's constant times the frequency. We'll come back to the rest of this in a moment. So the light wave is a self-propagating electromagnetic, it can also be described as a self-propagating electromagnetic wave. This wave has mutually perpendicular electric and magnetic field components. The electrics and magnetic fields are perpendicular to one another and to the direction of propagation. So that's schematized here. Note that although it shows the electric field as sort of having spatial, right? This arrow is supposed to represent a spatial axis. The way this is schematized, it sort of makes it look as if the electric field has spatial extent. Well, of course, that's not what that's supposed to represent. What that is supposed to represent is the magnitude of the electric field along this line. That's the red, and the blue represents the magnitude of the magnetic field along this line. And so they're using this sort of spatial representation to encode different information. They're using it to encode the direction and the magnitude of the electric field. It's not that the light wave necessarily has that spatial extent. This is encoding the electric field and the magnetic field along the line. Now, fundamental characteristic of a light wave is its frequency. The frequency would be the spatial distance from one peak to the subsequent peak along the wave. As we said before, that is in different regions of the electromagnetic spectrum. Of course, they're characterized by different wavelengths. The wavelength, bear in mind, is well, the product, as I said earlier, the product of the frequency times the wavelength is the speed, which in a vacuum is invariant due to fundamental physical laws. So we do want to just look quickly at some simple mathematical relationships, really to get at the nomenclature here. So we're going to use lambda to represent wavelength quite generally. Nu, this looks like a V, but it is well, it is typically in physics called nu, which is the Greek letter, a Greek letter, and so very commonly nu will be used for frequency, and almost invariantly lambda will be used for wavelength. Now, in physical, in the math describing waves, it's very convenient. They use trigonometric functions. It's very convenient, therefore, to describe to work in radians. If nu is the number of, right, so frequency would be given as waves per second. Every time there's a wave, you go through 2 pi radians. So 2 pi times nu would be the number of radians per second. So if nu times lambda is c, and we want to bring in 2 pi to scale the nu, we have to divide the wavelength by 2 pi. And so that gives us new units that will be used frequently sometimes in publications on spectroscopy and frequently in developing mathematical relationships related to spectroscopy. The 2 pi times nu gives you the angular frequency, which is radians per second. Right? Nu is waves per second, omega is radians per second, 2 pi nu gives you omega. This quantity, wavelength divided by 2 pi, is referred to as lambda bar. You'll see that later on. That's actually used rather commonly in vibrational spectroscopy, which is why I wanted to tell you about it now. This is now expressing wavelength rather than in meters per wave. A wave, of course, has 2 pi radians in it. This is meters per radian. So by rearranging this very simply, we see that nu equals c lambda to the minus 1, right? Frequency, we divide through by wavelength over here. We get frequency equals speed of light divided by wavelength. So that means that frequency is proportional to the reciprocal of wavelength. This is certainly obvious at a certain. This is obvious at a certain level. However, the reason I'm showing it here is because, in fact, this unit of reciprocal wave numbers, or waves per meter, is used in spectroscopy literature, and infrared spectra are often displayed, typically actually displayed in this sort of weird unit. And so the important thing to remember about it is that it is of course scaled by the speed of light. It is directly proportional to frequency. Higher wave number, higher frequency. We can now divide, we can now actually multiply through this thing by 2 pi, and we would get, or we could come over here and divide through by lambda bar, as it's called, and we would get the radial frequency is equal to the speed of light times the lambda bar, the wave number expressed in radians, or the number of radians per meter. So all of this terminology will appear in some spectroscopy literature. And infrared spectra are actually generally plotted as either wave number, lambda bar, either wave number, waves per meter, lambda to the minus 1, or lambda bar to the minus 1 radians per meter. Remember, both of these units are essentially proportional to frequency, so it's a frequency-like unit. The photon energy is quantized. We talked about this earlier. So the value of Planck's constant in using different energy units is given down here. The energy of a photon has to be exactly h times nu, the frequency in waves per meter. We can translate that to a radial relationship. Essentially, we want to multiply frequency by 2 pi and divide h by 2 pi. And so when we multiply frequency by 2 pi, we get angular frequency omega. When we divide h by 2 pi, we get something called h bar. So you will also see that it's simply Planck's constant divided by 2 pi. And of course, the relationships above tell you that the energy of the photon can also be expressed as h bar times the speed of light times lambda bar to the minus 1, or radians per meter, the reciprocal of lambda bar to the minus 1, which is units of radians per meter. Again, it's a frequency proportional unit. All right, so that covers the basic properties of light that we need to be familiar with to understand what comes next. So we'll move on. The next thing we've got to understand about are dipoles, right? And so now, I guess you could say I did talk about a little bit of the math in the previous slide, but only because it was closely related to the nomenclature. I'm now going to pretty much skip the math other than to qualitatively summarize the big point. The big point here is that for the electric field of light to do work on a molecule, it has to push around the charge. Right? Earlier in the course, when we discussed thermodynamics and the first law of thermodynamics, we looked at the physical definition, or the physicist's definition of work. Work is force times the distance over which it's applied. Work is the amount of work done is equal to the amount of energy transferred in some physical process. Spectroscopy involves light interacting with matter. Typically what's going on is the energy and the photons of the light are being used to change something about the energy state of a molecule. In visible spectroscopy, the photon is typically moving the molecule from one electronic quantum state to another. In vibrational spectroscopy, the light will move the molecule from one vibrational quantum state to another. We'll talk about the qualitative details of that shortly. The important point is for any of those energy transfer processes to occur, light has to do work on the molecule. Now, actually, the magnetic component of electromagnetic radiation can, in some cases, do work, but in the most common forms of spectroscopy, it is the electric field component of the light that is doing the work. Later on in the presentation, when we come to circular dichroism spectroscopy, we'll see the magnetic field does play a role in some cases, but those are actually small, as will be emphasized in that section. Those are small signals. Those are weak effects that are actually difficult to measure. The strong absorptions are generally those driven by the electric field. So for the electric field of light to do work on a molecule, well, what does an electric field do? Electric field pushes on charge. For the electric field of light to do work in changing the quantum state of a molecule, the electric field has to push the charges in that molecule around in some way, because work is equal to force times the distance over which the force is applied. The electric field produces a force on charged particles. So for the electric field to do work on a molecule, it must push the charged particles around. What we will see is this means that for light to be absorbed by matter, there has to be a change in the internal distribution of charge in the molecule. We are going to quantify the internal distribution of charge in the molecule by something called a dipole moment. The dipole moment is the first spatial moment of the charge distribution. A very simple way to think about it is as the sum of if you had a set of point charges, you can calculate the dipole moment which is done down here. With a set of point charges, the dipole moment is quite simply given as the sum of each charge times the vector to the position of that charge. When we go to a continuous charge, of course, molecules do not have, in general, some of them might have little things that sort of roughly approximate a point charge, but the vast majority of molecules, the ones we're interested in, for instance, water, it does not really have point charges. It has continuous charge distributions over the spatial extent of the molecule. And so in that case, the dipole moment comes from taking a spatial integral, a volumetric integral analogous to this sum, but where the charge density at every point is weighting the vector to that point, and then that volume integral gives you the dipole moment of the molecule. We'll talk about the math of dipole moments in depth in another presentation. Why do we care about this? We care about this because it can be shown, and has been shown in what is necessarily true for a light wave to be absorbed and transfer the energy of its photons to a molecule. The probability of the light wave doing that work and transferring energy to the molecule is given by the dot product of the electric field with something called the transition dipole moment. So this is key. The dot product of the electric field of the light wave times this change in dipole moment. Delta D is supposed to be the change in dipole moment. And so what this means is that the probability, the efficiency of the electric field of light transferring energy into a molecule, which is sort of the fundamental process involved in spectroscopy. The probability of that depends on the change in the dipole moment, right? This delta D is key. So what is delta D? Delta D is the change in the dipole moment. So the change in the dipole moment in the course of in going from one molecular state, one electronic state, one vibrational state to another. When the molecule changes its state, as we'll come back to later on, the electrons will move around. When the molecule starts vibrating more extensively, the charges move around. So when the molecule goes into a different quantum state, electronic or vibrational, the charges will move around. When the charges move around, right, the charge of the molecule doesn't change, right? There's no net charge being transferred to the molecule when the light does work on it. The charges are basically the same, their positions change, right? The total amount of charge, the integral of the charge density has to remain the same, but the position of the charges changes in the course of the transition. And so what that means is the dipole moment will change. That change in dipole moment in the energetically excited state compared to the ground state is delta D. The transition probability, the efficiency of the absorption process, is given by the dot product of the electric field vector of the light with the change in the dipole moment of the molecule in the course of the transition. So let's say that again, very important. The change in the dipole moment in the course of the transition. It will be a vector quantity because the dipole is a vector quantity. The dot product of that with the electric field of light squared gives the probability of the transition. Now, this is absolutely fundamental. You cannot understand much about spectroscopy at a research level, even at more than like a completely, beyond the fact that the energy involved in the transition has to equal, h nu. You can't understand almost anything about molecular spectroscopy without understanding this principle. And so to understand this principle, we need to know what a dipole moment is. And so that's a bit complicated. It's generally not treated in introductory physical chemistry texts. Oops, not quite sure what happened there. Sorry about that. Get back to the screen, back up here. It's generally not treated in introductory physical chemistry text. And so introductory physical chemistry texts in general do not really prepare people to understand fluorescence spectroscopy, because fluorescence is incredibly widely used in biology and biochemistry and biophysics and incredibly useful. That's something we really have to do, which is why we're going to dig into the dipole math so we can understand enough about this. And there are other ways in which dipoles and the change in the dipole in a transition plays into fluorescence. So that's the motivation for dragging you through what the next several slides drag you through. So what those do is they, before I go on to that, this stuff is also directly related to what makes lasers work. We don't really have time to talk about in this class. I put up a brief description of some of that here in case you're interested in it, but I'm going to skip that for today. Okay, so what we want to do, again, the key point here is that the change in the dipole moment of a molecule is what determines the magnitude of an electronic absorption or vibrational absorption. The efficiency with which light interacts with matter and transfers energy to it. How much light can be absorbed by matter depends on the change in the dipole moment during the absorption. So we need to know what a dipole moment is. So what is a dipole moment exactly? So I'm not going to go through the math here, but effectively it describes the electrostatic field of a charge distribution. Again, the reason we care about this is because the probability of the light-driven transition depends on the change in the dipole moment. So we can define the electric dipole moment. We talked about that a few minutes ago. It's simply the sum over, if it's a point charge distribution, the dipole moment is given by the sum over the charges times the vector to the position of the charge. The corresponding spatial integral would describe the dipole moment for something like a molecule which has a continuous charge distribution. The important thing is that the dipole moment has an electric field. The electric field is described quite simply by the dot product of r. In this case, this will be shown explicitly on the next slide. R is the distance from the point of observation to the coordinate system in which the dipole moment is defined. D is the dipole moment, defined up here. In many aspects, we won't talk about this directly. We will talk about it indirectly with fluorescence resonance energy transfer. The energetic interaction between dipoles can be derived from an extension of the math used to derive the dipole moment. Dipole interactions are tremendously important in physical chemistry. In nuclear magnetic resonance, of course, there is no such thing as a magnetic monopole. Magnetic species are inherently dipolar. We don't have time to talk about that in this course this year, but in nuclear magnetic resonance, dipolar interactions are what it's all about. But in optical spectroscopy and vibrational spectroscopy and fluorescence spectroscopy, there's still an important role of dipoles. Dipoles will interact with one another energetically. Why? Well, because the dipole has an electrostatic field. Of course, the dipole involves a spatial distribution of electric charge. So if you have a spatial distribution of electric charge, it will interact with an electric field. And so the interaction of energy of two dipoles is given by actually a relatively simple expression involving the vector quantities describing the individual dipoles, and then r, again, the distance between them. So we're not going to talk about this in detail now, but just a separate screencast will cover that. Sort of very at a conceptual level, where the hell does this come from? What is the dipole moment? So the dipole moment is the dominant term after net charge in a Taylor expansion of the electric field of a charge distribution. So the dipole moment comes from something called a multipole expansion of an electric field, and that's described in the next slide. Again, these slides are formulated to be really sort of study notes more than a textbook. But anyway, that's why I'm now stepping through in this presentation what's the point, and then we'll have separate presentations that focus down on the math for individual things. So the model here is that, well, the thing you're trying to capture. So if you have a spatial distribution of charge, right? That's schematized down here, Q1, Q2, Q3. These are supposed to be separate point charges in this case. And they're in some coordinate system that has an origin near the charges. What we want to do is now move far away from that charge distribution. And we want to understand, we want to quantify, because it's physics, we want to know the numbers. We want to quantify the electric field at a distance away from the charge distribution. And we want to do that in a simple way. And so, of course, what the math here will show is you could calculate this exactly based on just applying Coulomb's law to each of the individual particles. But you get some real conceptual simplifications and some real useful tools out of, instead of, just doing an explicit Coulomb calculation on every charge. Actually, you can see it would be very hard. For point charge distribution, it would be very easy for us to calculate the electric field over here, just using Coulomb's law applied to each charge. What if this were a continuous charge distribution? Then it would be much harder to calculate the electric field on that basis. And so there's something called a multipole expansion, which is a mathematical technique to approximate the electric field of either discrete or continuous charge distribution. So what this multipole expansion does, again, it's describing, in this case, I'm actually going to calculate the potential. Of course, the electric field is related to the potential. This is something different. Essentially, the potential, as we talked about earlier, is the energy involved in moving a charge. The potential reflects the energy that will the energetic changes that will happen when you move around a charge in an electric field. So what we're going to do is we're going to then describe the electrostatic potential of some charge distribution. And we're going to break it down according to things that we're going to call a monopole, a dipole, a quadrupole, and an octopole. The monopole is simply the sum over the charges. That's just the net charge, right? So the net charge divided by the radius, right? At very long distances, whatever the net charge is here is all we care about, right? So suppose that here you have two positive and two negative charges. If you go and so the net charge is 0. If you go very, very far away, all you're going to see is that the net charge is 0, right? So this is an approximation. If you go far enough away, right? So here we're looking now, R, I don't want to talk about the mathematical derivation, but R is supposed to be the vector from the origin of this coordinate system in the molecule to the point of observation. And so R here reflects the distance, the magnitude of that spatial vector, which is the distance from the observation point to the origin of the molecular coordinate system. So what we do is we have a term in this expansion of the electrostatic potential that's proportional to 1 over r, the first power of the reciprocal of the distance. And then we have a term that's proportional to the third power, and then we have a term that's proportional to the fifth power. So what happens as r gets large? Well, if r is very large, these third power and fifth power and seventh power terms will all be insignificant compared to the first power term. So if r is large enough, we can approximate this just based on the sum over the charges, which is the net charge, right? That makes sense. If we go far enough away from this, we're not going to see the internal structure. We're only going to see the net charge. Where this becomes clever and useful is when we get to intermediate distances. As r gets shorter and shorter, you can see that the r cubed term at some point will become significant compared to the r term. If we get down to an even smaller distance, the r fifth term will now become significant compared to the first power and third power terms. And so what this does for us is it gives us an approximation of the electric field of the light, the electric field of the, well, actually in this case of the potential energy, the electrostatic potential energy of the charge distribution at a varying distance from the charge distribution that we can get to be more accurate depending on how far away we are and what degree of accuracy that we want, right? As we include the higher order terms, they are going to be assuming the radius is greater than 1 in whatever system of units we're using on. The higher order terms in general, unless we're getting very close to the molecular coordinate system, the higher order terms in general will make a smaller contribution than the lower order terms, right? So in general, 1 over r to the 7th is going to be smaller than 1 over r. As r gets smaller, however, these things will become, the higher order terms will become larger in their relative magnitude. And so what will happen is, depending on what degree of accuracy we want and where we are in terms of distance from the molecule, from the molecular coordinate system, we can get an increasing degree of accuracy that suits our needs according to where we are by including additional terms in this so-called multipole expansion. The multipole expansion is essentially a three-dimensional Taylor expansion of the electrostatic field of the charge distribution. So that's what the math over here tells you. For the moment, let's not worry about the math. Let's just look at the take-home message. The take-home message is the strongest term here is just going to be given by the sum over the charge, the net charge divided by the distance to the point of observation, right? That's completely sensible. If you go far enough away from this, all you're going to see is the net charge. This is the equation we derived in an earlier class module for the electrostatic potential of some charge, net charge. And so this is simply reflecting the electrostatic field of the net charge. The cool thing is, as we get closer, this r cubed term will become more significant. And so what we can do is we can get a better approximation of the electrostatic field of the charge distribution by including this dipole term. So the dipole term is the most important the largest term in the multipole expansion, describing the electrostatic field of the charge distribution. So the dipole moment is incredibly useful because if we want greater accuracy from a further distance, or if we want to maintain accuracy in understanding the electric field as we get closer, we can now incorporate the dipole term. If we want to get still more accurate, we can incorporate the quadrupole term. But this dipole term is tremendously important because the length scales at which sort of molecular phenomena take place end up being such that the dipole moment is generally a very important contributor, whereas the higher order quadrupole and octupole terms generally are much less important. And so the dipoles play a tremendously important role in physical chemistry and especially in fluorescence spectroscopy, which is why they're going through them. So for the moment, that's all I have to say about dipoles. And again, we're going to skip the math because the math will be treated separately. This is just about the qualitative conceptual points, and that's the most important qualitative conceptual point. We can, again, we can do a we can do a Taylor expansion of the electrostatic field of a charge distribution. From that, we can get the electrostatic potential energy of the charge distribution. The Taylor expansion breaks that down in terms that have increasingly large exponents on the reciprocal of the distance. And so as we go from further away to closer to the charge distribution, the higher order terms in the multipole expansion become more and more significant. But over a very, very large range of distance, over the range of distances that is of the greatest importance in molecular science, the dipole term will dominate. And so the dipole is the sum for point charge distribution. It's the sum over the charges weighted by the vector of their positions. For the continuous charge distributions, it's a three-dimensional integral capturing that same property. It's the local electrostatic charge density. It's the vector to some point in the molecule weighted by the electrostatic charge at that point, integrated over the spatial extent of the molecule. Once we calculate the dipole moment, we can very easily calculate the electrostatic potential at any point in space attributable to the dipole term. And if we have two dipoles, there's a small extension of this that gives us the dipole interaction energy. Okay, so that's the important qualitative conceptual material here. Now, points that I did not make in class, but that are important to sort of keep in mind as we go forward, and then to remember later on. And so now this slide emphasizes some sort of important properties of the dipole moment, again, that are relevant to understanding spectroscopy, and that will be covered actually, these points will be covered in one way or another on both tests. They'll be covered on the short answer test the multiple choice test, and they also will be covered on the take-home test. So derivations related to actually two of these points it will be asked to derive two of these points to show that two of these statements are true mathematically. That will be an exercise on the take-home test, and you expect to know these points on the true-false test because they're incredibly important points in terms of the practical applications of all of this theory and in terms of molecular spectroscopy. So in general, the value of the dipole moment of a charge distribution depends on the choice of origin for the Taylor expansion, right? So the dipole moment is going to be the spatial integral over the positions of the charge relative to the origin. We change the origin, the dipole moment changes. That might seem a little bit weird, but don't worry about it now. So important points, though, that you can prove, and you'll be asked to prove, or that the value of the dipole moment is independent of the choice of origin if the net charge is zero. So if there's no net charge here, if all the individual charges cancel out to have a net charge of zero, you can show mathematically that at that point the value of the dipole moment no longer depends on the origin. So that's an important point practically in molecular science. The other important point, the change in the dipole moment due to rearrangement of a set of charges is independent of the choice of origin. So something called the transition dipole moment, which will be explained probably in the next PowerPoint, next screencast, that is independent of origin. The transition dipole moment, well, I did explain it, sort of crudely earlier on. The transition dipole moment is a sense the change in the dipole moment during the molecular quantum mechanical transition, right? We referred to that earlier. The probability of light transferring energy and being absorbed by a molecule is proportional to the square of the dot product of the electric field of light with the change in the dipole moment of the molecule during the transition. So that change in dipole moment, right, during a transition charge, when electrons move around in a molecule, charge will not be added or lost. When molecules start vibrating more, charge will not be gained or lost. You'll have the same total amount of charge in the molecule. So when the dipole changes in the course of the, right, in the light wave does not carry net charge, so it cannot put charge into the molecule or take it out, right? So the charge in the molecule is unchanged during the light-driven transition. So you can prove mathematically, and you will be asked to prove mathematically, that if the total charge in the molecule does not change, that during a structural rearrangement, that the change in the dipole moment is then independent of origin. It's, of course, the change in the dipole moment that's most important in terms of spectroscopy. So from the application to spectroscopy, the dipole moment, well, the change in the dipole moment is independent of the choice of origin. So the change of the dipole moment is objective and well-defined and doesn't matter where you put the origin. If there's no net charge, the molecular dipole moment also does not matter in terms of choice of origin. But for the general molecule that has net charge, and it has a continuous charge distribution, the value of the molecular dipole moment actually does depend on the choice of origin. That might seem weird, but don't worry about it for now. I think the key points is probably the most important point is this third one, the change in the dipole moment during a structural transition in a molecule. When the charge isn't changing, the change in the dipole moment is going to be independent of choice of origin. So that's going to be like defined. That will be precisely defined, irrespective. That change in the dipole moment will have exactly the same value, irrespective of where you put the origin for the Taylor expansion. All right. When we go through the math, we'll come back to this and review that material one more time. All right. So the next thing we're going to do is think about how all of this relates to vibrational spectroscopy. In vibrational spectroscopy, even at a very advanced level, you actually model bond vibrations as masses on a spring, the so-called Hooke's law spring. We looked at this earlier. The next screencast will pick up here and talk about vibrational spectroscopy, and we'll progress to actually a pretty sophisticated treatment of vibrational spectroscopy very quickly, and so that will be the topic of the next screencast.